This is my assistant SI Snuffleupagus. He has a lot of energy and has been running through my videos, so I thought I'd introduce him. Say hi, Snuffles. Okay. So this is my assistant SI. Whoa. So this is my assistant SI, Snuffleupagus. He's been running through all of my videos so far. So I thought I'd introduce him. He has a lot of energy, so he'll probably show up a little bit more. So, hey, what? Say hi, Snuffles. Oh, hush. This is my assistant SI, Snuffleupagus. He's run through like all of my videos so far because he has lots of energy and doesn't know how to mind his own business. Oh, don't growl at me. Shh. 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 Snuffles. Okay. So we're going to talk about lung volumes now. We briefly mentioned during our discussion of inspiration and expiration that lung volume increases when we breathe in, when we inspire, and decreases when we breathe out or expire. But this is a more detailed explanation of the different volumes that are associated with this. So to understand this line better, every increase you see is inspiration and every decrease you see is expiration. This is one cycle of breathing. So breathing in, breathing out. These volumes are broken down in terms of how high they go and how low they go. So a typical breath, you breathe in, you breathe out. When you breathe in, you still have more lung space left. When you breathe out, you still have more air that could have gone out. So this right here, looking at the moderate increase and the moderate decrease, is called the tidal volume. The tidal volume is the amount of air that goes in and out of your lungs in one normal breath. Tidal volume. So what about those breaths where you breathe in really deeply? Kind of like that. So that's going above and beyond what you normally breathe in. So where does that extra space come from? So that extra volume above and beyond our tidal volume, so from the peak of a normal breath to the very most that our lungs can hold, this is called the inspiratory reserve volume, also known as the IRV, just because I don't have that much space. So that's what the volume is called when we breathe in more than we normally breathe in. What about when we breathe out more than we usually breathe out? So if inspiration is inspiratory reserve volume, what is the reserve volume for breathing out more than we normally breathe out? So from the bottom of a normal breath to the most we can breathe out is called the expiratory reserve volume. ERV. So from the top of the inspiratory reserve volume, which is the most we can breathe into our lungs, to the bottom of the expiratory reserve volume over here, which is the most we can breathe out of our lungs, this is called the vital capacity. So from the top over here to the bottom over here, whoops, this is the vital capacity. The vital capacity is all the working space in our lungs that we have to breathe air in and breathe air out. So if we look at the inspiratory reserve volume, the tidal volume, and the ERV, these are the three components that make up our vital capacity. So to break down the IRV, the vital capacity is equivalent to the expiratory reserve volume plus the inspiratory reserve volume plus the tidal volume. So vital capacity is all three of these components added together, top to bottom. But if you notice down here at the bottom, we still have a little bit of space left before we've used up the entirety of our lung volume. This is just, down here at the bottom, the reserve volume. So we don't typically use the reserve volume. I don't think we ever use the reserve volume. Most air that we'll ever be able to get out of our lungs is from the expiratory reserve volume. If we add together the vital capacity and the reserve volume, we get our total lung capacity. And these are lung volumes. Now we're going to talk about partial pressures of oxygen and CO2, and then segue with that into hypo and hyperventilation. So as we've discussed over and over again this semester, things in physiological systems go from high concentration to low concentration. The flow of oxygen and CO2 through respiration is no different. So when we're coming from the lung and trying to when we're leaving the lung, we've just taken a breath of air, brought oxygen into our lungs, and allowed this oxygen to exchange into our vessels. So to travel from our lungs, our alveoli, into our vessels. And similarly, at the same time, CO2 has left our vessels and exited our body through our lungs. So when we're leaving the lungs, our blood's going this way, so around in a clockwise circle for reference. When we're leaving our lungs, do you expect CO2 to be high or low? And what do you expect oxygen to be? So think about that for a second, pause if you have to, and then come back. So when we're leaving the lungs and entering the tissues, because between exiting our lungs and then entering the tissues, nothing's really happened to the concentration of solutes in our blood, we're going to see a high concentration of oxygen leaving the lungs. So at about 100 millimeters of mercury, concentration of oxygen, just for the sake of argument, we're going to draw oxygen concentrations in dark blue and CO2 concentrations in light blue, just to keep track of things. So exiting the lung, we have a relatively high concentration of oxygen, and we're going to see a relatively low concentration at about 40 millimeters of mercury of CO2. The reason for this being, when we take a breath, oxygen enters our alveoli and then goes from the alveoli into circulation, and CO2 goes from circulation to the alveoli so that it can be expired. However, when we reach our cells have a much lower concentration of oxygen than we do in circulation. So when this blood reaches the cells, we're going to see oxygen going into our cells, and the opposite's going to happen for CO2. We're going to have CO2 leaving our cells. So again, I want you to take a second to think, if oxygen's entering our cells and CO2 is leaving our cells, once we leave the tissues of the body and start heading back towards the lungs, what are our concentrations going to look like? Okay, so we've had a lot of our oxygen go into our tissues to be used for metabolism, cellular functions, whatever it needs to be used for. So we're going to see this concentration, this partial pressure of oxygen, drop dramatically. So our partial pressure of oxygen is actually going to drop to 40 millimeters of mercury. So that's quite a dramatic drop from the 100 that we saw it at before. CO2, opposite of oxygen, is going from our cells and into circulation. So we're going to see an increase in the partial pressure of CO2. This isn't quite as dramatic as the change that we saw for oxygen. Our CO2 only increases to 46 millimeters of mercury. So these are the numbers she gave us last semester. As you know, professors sometimes change their minds on the specifics of things like this. So if she gave you different numbers this semester, those are the ones that I would go off of. The most important thing to remember here is we're going from high concentration to low concentration. So when we're going from circulation into the cells, we want oxygen concentration to be high and CO2 to be low, so that our oxygen can go into our cells to be used for metabolic processes. And our CO2, the waste product of these metabolic processes, can go into circulation to then be expired by the lungs. And then when we get to the lungs, we want oxygen to be able to come into circulation. So we want a lower partial pressure of oxygen when we reach the lungs and a higher partial pressure of CO2 so that it can go from circulation into the lungs to then be expired. So then these partial pressures don't work in a vacuum. They're not always perfect. They're going to increase or decrease above or below what we want them to be based on how quickly we're breathing. So this is where the concept of hypo and hyperventilation come in. If we're breathing super slowly, the purpose of breathing is to bring oxygen into our circulation and get rid of CO2. So take a second to think, do you think that this side of normal, so the left side of normal, or the right side of normal will be hypoventilation? So for hypoventilation, we're going to be looking at the left side of normal. So at a normal respiratory rate, you have a relatively high concentration of oxygen, partial pressure, and a relatively low partial pressure of CO2. If we're not breathing enough, we're not bringing enough oxygen into circulation, so you're going to see a super low partial pressure of oxygen because it's not coming in, and you're going to see a really high partial pressure of CO2 because your body's not able to breathe quickly enough to get rid of the CO2 that's being built up through metabolic processes, so it's going to continue to build up in your bloodstream. The opposite is true of hyperventilation. So hyperventilation is going to be the opposite side, the right side. With hyperventilation, you're breathing really quickly. And when you breathe super quickly, yes, you're getting a lot of oxygen in your system, so you're going to see that increasing dramatically above normal, the partial pressure. You're also going to see the partial pressure of CO2 drop dramatically because as you breathe more quickly, you're able to breathe out the CO2 faster than your metabolic processes are able to produce that CO2. And as we'll see a little bit later, this can be an issue based on how CO2 is transported in the blood. Okay, so when oxygen is transported in the blood, it's transported on red blood cells by a protein called hemoglobin. So these heme proteins, as I've drawn in the middle of a red blood cell here, carry oxygen very cooperatively. So one thing you'll notice about these proteins is that they're very all or nothing. One heme protein is capable of carrying or transporting 4 O2 molecules. So 4 O2s. And with this cooperativity, you will rarely see a hemoglobin, if ever, transporting just 1, 2, or 3. It'll either transport no oxygen molecules or 4 oxygen molecules. So then an important thing that people study is how oxygen binds to hemoglobin at different partial pressures of oxygen in the blood, which is what this graph right here looks at. This is looking at oxygen saturation of hemoglobin, so our y-axis here, as a function of the partial pressure of oxygen in the blood. So an important thing to note here is as the partial pressure of oxygen decreases, so as we go this way on our graph, we're going to see our oxygen saturation of hemoglobin increase to a certain point. There comes a point where all of our hemoglobin is saturated because we only have so much hemoglobin in our blood, so that we can't load any more hemoglobin with oxygen. So once we reach a certain point up here, we see our curve flatten out regardless of what the partial pressure of oxygen is in the blood. So yes, this curve increases as we go along. I've noted here the partial pressure of oxygen of 40 millimeters of mercury and the oxygen saturation of 80%. That's because this 40-80 right here is the optimal partial pressure and percent saturation for unloading into tissues.